Hello, my name is Paul Greenlow. I'm a 5G solutions architect with Comdex. I will be providing an overview of 5G technology. The topics that I will be discussing are evolution of mobile networks. We'll look at the evolution from 1G to 4G before we get into the aspects of 5G. We will look at emerging trends. We will discuss some of the 5G use cases. We'll be discussing as well the drivers for 5G and the benefits it brings to operators and vendors. We will talk about the trend in cloud native and microservices and how 5G benefits from those trends. We will talk about 5G new radio frequency bands. We will highlight some of the 5G RAN capabilities, 5G security capabilities. We'll discuss what the 5G QoS model is all about, and we will conclude with a comparison between 4G and 5G. So let's talk about the evolution of mobile communications. Back in the 80s, 1G was introduced to the marketplace. Its main focus was to provide voice service with mobility. It did not have support for data or SMS service. One of the biggest drawbacks was the lack of interoperability among vendors. This made the service very expensive to the end user. In the 90s, 2G was introduced to the market. It provided higher capacity in support for voice, data, and introduced SMS service. Unlike 1G technology, 2G was based on standards and allowed for interoperability among different vendors. It also allowed the user to select among different mobile devices, making the service more affordable. All carriers that implemented the same standard technology could offer their users roaming services. There were two main standards for 2G, GSM and CDMA. In general, both offer excellent call quality and data speeds up to 14.4 kilobits per second. GSM evolved to GPRS, General Packet Radio Service, adding enhancement for IP packet forwarding, reaching rates up to 171.2 kilobits per second. The technology used an overlay approach where voice was sent to an MSC using TDM technology and data was sent to an SGSN via IP. 3G then became available in the 2000s, providing support for even faster transmission and higher data rates, with average speeds of 384 kilobits per second and theoretical downloads of up to 2 megabits per second, good enough for web browsing services. 3G allowed network operators to offer a wider range of more advanced services by reaching greater network capacity through improved spectral efficiency. Typical services included wide area wireless voice telephony and broadband wireless data, all in a mobile environment. From this point on, 3GPP standards became the Bible for all vendors and carriers that wanted to compete in the mobile space and needed to follow the evolution of the technology from the perspective of the device, the RAN, and the core. The 3GPP body of standards introduced 4G, which was based on an all-IP flat network architecture. As such, it was able to provide an optimal network that can guarantee end-to-end communication for different traffic types. It's important to understand that network design became of greater importance for packet switch networks, and when done properly, it allows for optimal use of the network capacity to accommodate different services providing the proper QoS treatment. This is a major advantage over predecessors like 2G and 3G, which relied on TDM technology for voice services. 4G uses SIP as the signaling protocol to establish end-to-end communication and has proven to be an easy protocol to troubleshoot communication issues. The key technology breakthroughs for 4G are MIMO and OFDM. These two technologies enable the 4G network to provide bandwidth capacities to individual users of 100 megabits per second for applications that require high mobility and up to 1 gigabits per second for fixed connectivity. Let's look at the emerging trends in mobile communications. The evolving trend in communications is to move beyond consumer broadband, which was the highlight of 4G technology. There's greater need now to support extreme mobile broadband, ultra-reliable, low-latency transmission. There's also a great need to support devices beyond mobile phones, such as sensors, drones, meters, wearables, machines, video cameras, cars, etc. Let's look at the triangle in the figure. There are three main areas where use cases will fall under. Some will overlap depending on the complexity of the use case, but in general, let's look at these three areas. On the top, we have extreme mobile broadband use cases, which in general will require high bandwidth capacity, support for more devices per area, adequate latency for streaming services, adequate capacity for large data transfers. Examples of these use cases are fixed wireless and consumer mobility. Then on the bottom left, we have massive machine-to-machine communication use cases, which in general are associated with massive number of devices where latency tolerance is high, meaning transmission delay can be high. Use cases involving smart meters are an example of these use cases. Then on the bottom right, we have critical machine-to-machine communication use cases, which in general have low latency tolerance. Also, a requirement for high resiliency. Examples of these use cases are autonomous driving and industrial IoT. Use cases in general will be very unique in nature, and they will be associated with a unique set of requirements to address the different traffic types that compose the services to be provided. Smart meters can leverage 5G to enable remote monitoring and management of utility services, such as electricity, water, and gas consumption. This use case requires moderate capacity to transmit regular consumption data to the utility companies for billing and monitoring purposes. Smart meters are stationary devices and do not have mobility requirements. Tolerance for latency is high, given they do not deal with delay-sensitive traffic. They primarily deal with periodic data transmission. Resiliency requirement is low, given the nature of the application. 5G can facilitate vehicle-to-vehicle and vehicle-to-infrastructure communication, enabling a safer and more efficient transportation. Car-to-car communication requires moderate to high capacity to exchange real-time traffic data, vehicle status information, and safety information. Cars are mobile, and high-speed mobility support is crucial for seamless communication between vehicles on highways and urban areas. Tolerance for latency is low. Low latency is essential for car-to-car communication to enable rapid exchange of safety-related information and collision avoidance. Resiliency is critical to maintain continuous connectivity and ensure robust communication even in challenging environments or during network congestion. 5G-based fixed wireless access can provide high-speed broadband connectivity to homes and businesses without the need for physical cables. The use case requires high capacity to deliver high-speed internet access to multiple users simultaneously. There is no mobility requirement as it caters to stationary locations. Tolerance for latency is medium, given data involved can be video streaming, online gaming, and remote collaboration. The use case relies on resilient connections to provide stable and consistent broadband services, minimizing disruptions and ensuring reliable connectivity, but it is not as strict as in some industrial applications. 5G can enhance the mobile broadband experience for consumers, enabling faster speeds, increased capacity, and seamless connectivity. The use case requires high capacity to support bandwidth-intensive applications like video streaming, gaming, and social media. The use case requires high-speed mobility to ensure uninterrupted connectivity for users on the move, such as in vehicles or in trains. Tolerance for latency is medium. Giving low latency treatment is essential for responsive applications like online gaming, video calls, and live streaming. Resiliency is crucial to maintain consistent connectivity, reducing the chances of dropped calls or service interruptions. 5G can empower the industrial Internet of Things by connecting and controlling various industrial devices, sensors, and systems. This use case demands high capacity to accommodate a massive number of connected devices and enable efficient data exchange. The use case can have both stationary and mobile elements, requiring support for seamless connectivity and communications in diverse environments. Low latency is crucial for real-time monitoring and control of industrial processes, ensuring timely decision-making and optimizing efficiency. These systems rely heavily on a resilient connectivity to avoid downtime, maintain productivity, and minimize disruptions in critical industrial operations. So in summary, the use cases for 5G, such as smart meters, car-to-car communication, fixed wireless access, consumer mobility, and industrial IoT, have varying requirements for capacity, mobility needs, latency, and resiliency. 5G networks are designed to cater to these diverse use cases, enabling faster data transmission, real-time interactions, and reliable connectivity in each scenario. Although the technology is able to provide all this capability, proper planning and design is necessary for optimal and guaranteed results. Let's look at the technology drivers for 5G and the associated benefits. In the software landscape, there are two main drivers. One, the shift in software evolution to microservices, and two, the implementation of cloud technology. Software has evolved from monolithic to a microservices architecture. Let's take, for example, the AMF. This is the access and mobility function in 5G. From a network perspective, the AMF manages the mobility aspect of the UE. From a software perspective, this entity is broken down into smaller independent services that handle functions like load balancing, the service logic of the calls, and operations and management functions. Individual microservices can be upgraded without disruption to the network function. Services technology also offers the benefit of higher reliability and performance. Reliability and performance is really improved because the microservices architecture can be divided into stateless and stateful entities, each with its own redundancy schemes. As an example, service logic application is a stateless by nature, resulting in efficient processing of calls with n plus k redundancy operation. Another main driver is cloud native. The benefits of a cloud native architecture include infrastructure agnostic, which means the underlying hardware can be from any vendor. As such, an operator, depending on the application requirements, can select a private cloud, a public cloud, or a combination of both, without really any concern for what kind of hardware actually is being used. Cloud technology also enables orchestration and automation capabilities. The main enabler for for this is Kubernetes, which is the foundation for cloud technology and allows 5G network functions to be deployed without manual intervention. The technology is fully aware of the hardware resources that are available, and it also takes into consideration anti-affinity rules associated with the network function to guarantee its performance and reliability needs. Furthermore, APIs enable the Kubernetes to extend visibility and operations to other systems to enable advanced orchestration capabilities and automation. From a 5G perspective, there are a few key drivers that provide so much flexibility and capability to operators. Let's talk about some of them. One of them is separation of control and user plane. This means that control resources are deployed independent of media resources. The benefits from a scaling flexibility perspective is that if more media resources is required, only those network functions that handle the media are increased with no impact on the control functions. It is also possible to optimize placement of network entities in the network as required. For example, given that media traffic is typically exchanged among users at certain locations at the edge of the network, a network designer can place network functions that deal with media at the edge, while keeping the control functions in a more central location. Another technology driver for 5G is based on an open architecture model, which promotes the use of different vendor core network functions and the integration of third-party applications via APIs. It implements a service-based architecture that provides a secure means to introduce network functions into the environment and establish all the policies and services that will be offered as consumers and producers of the 5G environment. APIs are available to integrate to systems that can provide automation and artificial intelligence interaction in support of evolving use cases. As such, the 5G open architecture allows third-party systems to get real-time visibility on different aspects of the 5G environment, interpret and analyze the data, and make real-time operational decisions. 5G new radio frequency bands. 5G technology operates across three main frequency bands, referred to as low band, mid band, and high band. Low band runs typically below 3 GHz, including frequencies previously used by 4G networks. Low band frequencies provide excellent coverage and penetration through buildings and other obstacles. They offer wide area coverage and have the potential to cover vast geographic areas with fewer base stations. Low band frequencies have a lower capacity compared to higher frequency bands. They provide relatively slower data rates compared to mid and high band frequencies, although still faster than 4G LTE. From a use case perspective, low band frequencies are ideal for providing wide area coverage, especially in rural areas or suburban regions. They're suitable for applications that prioritize coverage and connectivity over extremely high data speeds, such as IoT devices, smart meters, and rural broadband access. Mid-band runs typically between 3 GHz and 6 GHz. Mid-band frequencies strike a balance between coverage and capacity. They offer a compromise between coverage area and data speeds, providing a good combination of both. Mid-band frequencies offer higher capacity and faster data rates compared to low-band frequencies. From a use case perspective, mid-band frequencies are good for providing enhanced mobile broadband and supporting applications such as video streaming, gaming, and consumer mobile services. High band typically runs above 24 GHz, including millimeter wave frequencies. High band frequencies offer extremely high data speeds and low latency, but they have limited coverage and are easily attenuated by obstacles like buildings and vegetation. They require a dense network of base stations to ensure coverage. High band frequencies provide the highest capacity and fastest data rates among the three bands. They can deliver multi-gigabit speeds, enabling applications with demanding requirements like augmented reality, virtual reality, and ultra-high definition video streaming. High band frequencies are suitable for dense urban environments, stadiums, campuses, and areas with high user density. They are utilized for applications that demand ultra-fast speed. It is important to note that the availability and specific frequency ranges of these bands may vary by country and regulatory environment. Network operators deploy a combination of low, mid, and high band frequencies to provide a balanced 5G experience that meets various coverage, capacity, and speed requirements. 5G RAN capabilities. In order to meet the extreme new requirements for high throughput, ultra reliable, low latency, and massive machine communication, it is important for the 5G new radio to be better than 4G. The table captures the main features of 5RAN to accomplish this. For apps that need high throughput, 5G RAN can achieve this via centimeter and millimeter wave bands, which was not possible with 4G. It is also important to understand that 5G implements massive MIMO, which is similar to 4G but to a greater scale, allowing transmission of multiple data signals at the same time over the same radio channel. 5G implements advanced technology that improves latency in the RAN. Furthermore, low latency is achieved with proper network design that leverages 5G flow-based QoS model and slicing. 5G allows massive connectivity of mobile devices and things by improving battery saving techniques. 5G can also guarantee reliability by having a unified access that supports end-to-end NAS signaling, not only for 3GPP access but also for non-3GPP access networks. 5G security capabilities. The 3GPP body of standards has made improvement to security in 5G. Authentication in 5G goes both ways. This means that not only the network verifies who the UE claims to be, but the UE also verifies the network as well. One key improvement over 4G is that authentication always happens via the NAS protocol for both 3GPP and non-3GPP access networks. This provides a consistent and easier way to debug the authentication process. This also means that the same authentication and encryption standards are applied, reducing potential security vulnerabilities. Authorization is another key aspect of 5G, as it was in 4G. The 5G network verifies that the UE is allowed the services it is requesting. It verifies aspects such as allowed access technology, access to a particular PDN, and requested QoS profile as well. 5G can protect the integrity of control and user traffic using encryption-decryption protocols. Using, for example, RAN encryption for 3GPP access, and IPsec for non-3GPP access. It's important to note that there are mechanisms that should be considered beyond 5G to detect and protect at different layers of the protocol stack when control of user traffic has been compromised. This is all part of a good end-to-end network design. 5G also implements mechanisms to provide privacy protection. The objective is to keep user traffic unavailable to other users, and it can do this by concealing the identity of the user and keeping private the location of the UE. Quality of service in 5G. In a traditional IP-QoS-enabled routing environment, IP packets are handled by routers in hop-by-hop fashion, and each router along the path provides proper handling to each packet based on the DSCP value in the IP header. This is all based on the DiffServ QoS model. In similar fashion, a 5G network needs to be able to differentiate traffic in the uplink and downlink direction and provide differentiated treatment. All the traffic associated to a user traverses the PDU session. QoS policies in the 5G environment will define the parameters that will identify all the IP flows for the user and its required treatment. The required treatment will be based on the assigned 5G QoS ID, which defines the SLA for a particular traffic type. Parameters include the resource type, priority level, packet delay, budget, maximum data burst volume, and default averaging window. Once a UE has established a PDU session, it will be able to forward traffic in the form of IP flows. So compared to 4G, 5G offers a more granular approach to offer QoS by allowing several IP flows per user to have differentiated treatment. Less signaling intensive because only a single PDU session is required to deal with all the user traffic. In 4G, several dedicated bearers need to be established to handle each IP flow. Let's look at the main differences between 4G and 5G. 5G is a more flexible and scalable than 4G technology. Unlike 4G, which is based on a point-to-point architecture, 5G supports a service-based architecture which brings operational benefits to the operator. In a service-based architecture, the network functions take the role of either a consumer or a producer, and as such all services and connectivity among the network functions is coordinated by a centralized entity. In this manner, there is no need for point-to-point provisioning, and the introduction and removal of network functions in the network is easier to control and manage. The 5G architecture takes advantage of software technology drivers such as microservices, which allow separation of stateless and stateful functions, which in turn can be distributed in the network with N+K redundancy. The result is a very reliable network with dedicated and independent network functions that reach optimal performance. The 5G quality of service offers a more granular mechanism to provide differentiated services with the use of less signaling to deliver IP traffic. In 4G, a dedicated bearer needs to be established per user for every service type, and in 5G only a single session is required. 5G also supports network slicing, providing another level of service differentiation and dedicated resources. One of the main strengths of 5G over 4G is its open architecture nature. The 5G environment can provide visibility and secure control to third parties via APIs. The security is provided via the network exposure function entity. Another major advantage of 5G over 4G is its unified access across 3GPP and non-3GPP access networks. 5G uses NAS signaling for these networks in a very consistent manner, providing true multi-access capability and wireline and wireless convergence.